In this video, we'll give the formal definition of the class NP. We'll see that the concept of polynomial verifiability is important in defining the class NP. And we'll also talk about the relationship between the classes P and NP. Let's begin with this concept of polynomial verifiability. So given some language, A for example, a verifier is an algorithm that is given some extra information, which we'll denote with the letter C, which the verifier can use to check and verify that the input string is in the language A. So we've got a problem of determining whether some string is in a language. It's a problem, and we've got an instance of the problem. And we'd like to know what the solution is, whether it's yes or no, or is there a Hamiltonian path, for example, or not. But the idea is that there's an additional piece of information denoted with the letter C, and a verifier is an algorithm that's a little bit different from just the membership testing algorithm. The verifier algorithm takes C as well as W, and it uses that extra information to verify that W is in A. So let's look at an example, and the example that we'll use is the Hamiltonian path problem. So remember the problem, that is, given a directed graph and two nodes S and T in the graph, is there a path from S to T in the graph that contains all the nodes, that passes through all the nodes? And we have an exponential program, an exponential algorithm that will solve this problem, and it appears that this problem is exponentially hard. I say it appears because we have an exponential algorithm, but we don't have a polynomial algorithm. So it seems like this problem requires exponential time. But we've also got the idea of a verifier algorithm. If we knew a path, okay, if we're given a path, and here's an example, 1, 3, 5, 4, 2, 6, 8, going through the various nodes in that order, then, so this is a path from some node S to some other node T, and we can confirm that it is a Hamiltonian path by checking to make sure that it's a legal path, and also by checking to make sure that all the nodes in the graph are in the path. So given C, we can tell whether W is a member of this language. In other words, given W, which is the graph and the starting and ending nodes, we can tell whether there's a Hamiltonian path. And we can do it in polynomial time if we have that path. In other words, we can verify that this is a solution. We can check that this is a solution. So here's a formal definition for a verifier that says essentially the same thing. Given a language A, or equivalently, given a problem A, we're wondering whether some particular string is in that language. The language is defined as the set of all strings W such that, and there's a definition for the language. But an alternative definition is that the set of strings made of those W's that are accepted by the verifier is exactly the set of strings that are in the language. So it's a verifier if it accepts W given C, for some string C, for every W that is actually in A. The set of strings that the verifier accepts for the C stands for certificate, so V is a verifier if, given W and C, it accepts exactly when W is a member of the language. The verifier V is an algorithm itself, and if it runs in polynomial time, then we say it's a polynomial time verifier. And so a polynomial time verifier runs in polynomial time with respect to the length of the string W. And we can just define a language as being polynomially verifiable. I can barely say it and barely write it here. A language is polynomially verifiable if it has a polynomial time verifier. As I mentioned, the string C is called the certificate, or sometimes maybe it's called the proof. We don't care really about the length of C, but note that a polynomial time verifier does not have time to read a certificate that is larger than polynomial in the length of W. So you can't have too large a certificate. Now we're ready to give the definition of the class NP. There are really two definitions and they're equivalent. So what we're going to do is we're going to present one of these as the definition of NP and the other as a theorem that they're equivalent. So let's start with this definition first. NP is the class of languages that have polynomial time verifiers. So we can see that the Hamiltonian path problem has a polynomial time verifier, so it is in the class NP. And so the other definition is that concerns a non-deterministic Turing machine that runs in polynomial time. And so we're presenting this as a theorem, and we're saying that they're the same. These two definitions are the same. So let me read this. A language is in the class NP if and only if it is decided by a non-deterministic polynomial time Turing machine. In other words, if the problem can be decided by a Turing machine, we allow that Turing machine to be non-deterministic, which gives it a lot of power, but the time that that Turing machine takes to run is polynomial in the length of the input, which means that the non-deterministic Turing machine may have a tree, a computation history that's a tree that has lots of branches, but all branches terminate and the longest branch is polynomial, and the length of the longest branch is polynomial with respect to the input length. So these are both definitions of NP. We're presenting one as the definition, so the other has to be a theorem that we have to, and we'll present next a proof that these two things are equivalent. In other words, that the if and only if holds. So here I say that in some treatments of this material, you see that this is the definition of NP. And after the proof, you can use either however you prefer, and this is oftentimes the way it's talked about, that the class NP is also a set of problems that can be decided in polynomial time on a Turing machine, but only if the Turing machine is non-deterministic. If it is a deterministic Turing machine that will decide, if there is a deterministic Turing machine that will decide the language in polynomial time, then the language is part of the class P. So the N stands for non-deterministic and P stands for polynomial time. And now for a proof that these two definitions of the class NP are equivalent. This was an if and only if theorem, so we need to prove two directions. So here's the first direction, and then next I'll show you the second direction. So given a polynomial time verifier, we need to show that there's an equivalent polynomial time non-deterministic Turing machine. So we need to give an algorithm for converting a polynomial time verifier into an equivalent polynomial time non-deterministic Turing machine. In the other direction, just ignore this part first, and the other direction is that assume we have a polynomial time non-deterministic Turing machine, we need to show how to construct a polynomial time verifier. So let's go up to the first part of the proof, the first direction. An equivalent polynomial time non-deterministic Turing machine. Well, here's the Turing machine. This is a non-deterministic Turing machine, so we get to non-deterministically guess things. Well, we have a polynomial, we're assuming we have a verifying algorithm that runs in polynomial time, so we can use that as a subroutine in this machine. So what we do, our algorithm is simple. We non-deterministically guess the string C. It's at most polynomial in the size of the input, so we guess it, and we can do that in polynomial time, of course. And then we run v as a subroutine on the input and this string C that we've just guessed. And if v accepts, we accept, otherwise we reject. So guessing the certificate can be done in polynomial time. Okay, we may have exponentially many strings, but because of the non-determinism and all the branching that we're allowed, we can create one string on a branch that's at most polynomial in length with respect to the length of the input. So we non-deterministically guess the string C on one branch of the non-determinism, and then we run v on the pair, and if it accepts, we accept, otherwise we reject. Okay, now the other direction. Assume we have a polynomial time non-deterministic Turing machine. We need to construct a polynomial time verifier. So the verifier will have as input W and C. Okay. What we do is we basically are going to simulate the non-deterministic Turing machine, but we're only going to follow one path. And the path we're going to use will be given by C. So we have a polynomial time non-deterministic Turing machine that decides this language. And we want to construct a polynomial time verifier. So we will construct such a verifier, and the verifier will take as input a certificate, and we get to define sort of the meaning or what kind of certificate we'd like to have. And so what we'll have is a certificate that tells us which decisions are the correct decisions in the non-deterministic Turing machine. So then the verifier does nothing more than use the certificate, which is a list of proper guesses on the computation history, and it simulates that one particular branch of the non-deterministic Turing machine, using the certificate C as a guide about which choice to make at each step. And if this branch of the computation accepts, then accept, otherwise reject. So again, just to repeat what we've done, we've shown that either of these two definitions of the class NP is equivalent to the other. So the first definition is that NP is the class of languages that have polynomial time verifiers. In other words, given an input and some hint of some sort, such as the solution or how we get there, then we can create an algorithm that in polynomial time will determine whether it's correct or not. The second definition is that a language is in NP if it's decided by some non-deterministic polynomial time Turing machine. So if it can be decided in polynomial time by a Turing machine and in general by a non-deterministic Turing machine, then it's in NP. These two definitions are equivalent. We gave this as the definition, and then we showed that this was equivalent in the proof. So we can look at the distinction between the class P and the class NP this way. In the class P, this is the class of languages for which membership in the language can be decided quickly. And by quickly, we mean in polynomial time. Quickly means in polynomial time with respect to the length of the input. NP is the class of languages for which membership can be verified quickly. And verified means that is given some extra information, which we call the certificate. We can quickly confirm, quickly meaning polynomially, confirm that W is in the language. And so think about the Hamiltonian path problem. Okay, if you're given just a graph and the starting and ending nodes, then you're left to just decide the question. But we could also be given a separate string, which is the actual path itself. So in this case, you can think of it as a solution, or you can think of it as a proof that the particular input is in the Hamiltonian path language. In this case, our certificate is the evidence, if you will. The evidence being a list of nodes that form the path itself. The question is whether the path exists, and deciding that is difficult unless, of course, you've got the path itself. So our certificate or proof that a particular graph contains a Hamiltonian path is the path itself. So that's the verified. So P, membership can be decided quickly with no other information. In P, membership can be verified quickly with additional information. Previously, we defined the class of languages that can be decided by a deterministic Turing machine. For example, time of n squared here indicates the class or the set of languages that can be decided by a deterministic Turing machine in order n squared time. And for every possible running time, we have a corresponding class of languages that can be decided by a deterministic Turing machine in n squared time. By analogy, we're going to define n time, n standing for non-deterministic. So, for example, this class here, n time of n squared, is the set of languages that can be decided by a non-deterministic Turing machine in order n squared time. So, a more complete definition of this notation is given up here. So, n time, where t is some function, is a set of all languages, that can be decided by an algorithm, by a non-deterministic Turing machine algorithm, in order t time. Okay, so these two definitions are analogous. One concerns deterministic Turing machines, the other concerns non-deterministic Turing machines. And so we have this definition of NP. Okay, here is the class of languages that can be decided in n time, n squared time, n cubed time, n to the fourth time, and so on for all n. For all k. Okay, and this is the union. So we're saying all of the problems that can be decided in polynomial time for any polynomial by a non-deterministic Turing machine. That is the class of NP. Let's give another example of a problem that's in NP. This is called the clique problem. A clique of people is a small group of people that all talk to each other. They have their own club or their own group, and these things form in grade school and high school, and where they tend to exclude other people. We have a more mathematical definition of clique here, and that's what we're going to talk about. Given a graph, and here we're using undirected edges, so you see no arrowheads down here. Given an undirected graph, a clique is a set of nodes such that every node in the clique is connected to every other node in the clique. So here is an example down here. Here we have what we call a 5 clique. Okay, we have 5 nodes, and every node is connected to the other 4 nodes. Here we have a 7 clique, and we have 7 nodes. And every node is connected to the other 6 nodes. 1, 2, 3, 4, 5, 6 edges coming out of every node. And in general, we can say a k clique is a clique with k members. So this is a 5 clique, this is a 7 clique. And now here's a problem. Here's a graph of undirected edges. Does it contain a 5 clique? Well, certainly 7 is not part of a 5 clique because it only has 3 connections, and 6 might be part of a 5 clique. Every node in the 5 clique should have at least 4 edges, 4 to the other nodes in the clique. This one has 1, 2, 3, 4, 5. I can see a 5 clique here. Perhaps it's easiest to see the star that forms between these nodes, like this. Okay, and the pentagram that goes around them, 5, 6, 1, 3, 4, 5. So the answer to this problem is yes, it does contain a 5 clique. So here's the problem in general. You're you're given a graph and a number, okay, for example, this graph and the number 5, and the question is, does that graph contain a k-click? And in this case, with the number 5, this graph does contain a 5-click, so this would be a member of the language, and the answer would be yes. Okay, it turns out that the click problem is in NP. Okay, we can prove that, and remember our definitions of NP. In order to prove that click is a member of this class of problems called NP, we can do it two ways. Since we have sort of two equivalent definitions of NP, we can provide the proof. We can structure the proof in two ways. We can provide a polynomial time verifier, or we can provide a polynomial time non-deterministic Turing machine that will decide the problem. So we have two ways to decide this problem, or to prove, I should say, to prove that this problem is a member of NP. I won't go any further with this click problem, except I did want to mention one more thing, which was that this general approach is true of many problems in proving they're a member of NP. There are two different approaches. Okay? For any problem, whether it's click or something else, it suffices to either provide a polynomial time verifier or provide a non-deterministic Turing machine that decides the problem in polynomial time. So this is not special to click. It's a consequence of the fact that we have two definitions for NP, and those two definitions are equivalent. Let's repeat our definitions of the class P and NP. The class P is a class of all languages that can be decided, or equivalently we could say the set of all problems that can be solved in polynomial time on a deterministic Turing machine. On the other hand, NP is the class of all languages that can be decided, or we can say equivalently the set of all problems that can be solved in polynomial time on a non-deterministic Turing machine. So, deterministic Turing machine algorithm or non-deterministic Turing machine algorithm. Now we come to an unsolved problem. This is an open question. This is a famous unsolved problem, and certainly the most well-known unsolved question in computer science. It's the question of whether P equals NP or not. So there are really two possible choices. The set of problems in P is equal to the set of problems in NP, or the set P is a proper subset, that there are problems in NP that are not in P. And it certainly seems that the latter is the case. We have exponential algorithms to solve the problems in NP, but we don't have polynomial time algorithms to solve those same problems. So it seems, by the empirical evidence, that the second condition holds, that these two sets are not equal. But it's absolutely surprising or baffling or mysterious or interesting that we don't have a proof that these two sets are equal or not equal. There are a lot of problems that are known to be in the class NP, and none of these problems today can be solved in polynomial time on a deterministic Turing machine. We have a lot of problems, like click and the Hamiltonian path problem, that are known to be in the class NP, and we have not found any solutions for these problems that will run on a deterministic Turing machine in polynomial time. These problems seem to require exponential time to solve. On a normal deterministic computer, these problems, like click and Hamiltonian path and many, many others, seem to require exponential time to solve. But we don't know that for sure. It's not known whether problems like Hamiltonian path and click and the satisfiability problem, which we haven't talked about yet, are in P or not. So this is an open question, and I think there's $1 million prize being offered to the person that can prove either one of these two possibilities. It may be that the reason we can't solve this problem at this time or answer this question is because we're not asking it the right way. Sometimes unknown problems get solved later on because the general understanding of the field not only increases but changes. We get a more sophisticated understanding of the terms perhaps, or we just learn to look at it in a different way. And so it seems to me that there's really kind of a third choice, which is neither of these, but that choice, and I don't know whether this is correct or not, but it seems that there's another choice, which is that the question itself is in some way ill-formed or doesn't make sense or invalid or overlooks something. So perhaps in the future we'll just determine that the question wasn't asked in the right way. But I think the consensus among people who understand this problem is that the latter option is the case, that these two sets are really different, and that problems like the Hamiltonian path problem and the clique problem must be done in exponential time unless you allow yourself to use a non-deterministic Turing machine, which of course is a theoretical construct and not like any real computer. So these problems really do seem to require exponential time to solve, but we don't know that they require exponential time. Let me be a little bit more careful when I throw things around like algorithms that require exponential time. And let's define x time as the set of all problems that require exponential time when run on a deterministic Turing machine. Here we see 2 raised to some polynomial. Okay, regardless of the polynomial, doesn't matter. So this is saying the set of problems that can be solved in polynomial time. I'm sorry. This is saying that the set of all problems that can be solved in exponential time on a deterministic Turing machine. So now I'm going to present some results that we have that so here's the relationship between these sets. And clearly P is a subset of in P. The question is whether it's a proper subset or not. Because every deterministic machine is a non-deterministic machine. And here we have exponential time because we can solve these problems in exponential time. So any problem in P can be solved by simulating the non-deterministic Turing machine in exponential time. So we have these relationships that must hold. Of course, but it's apparently the case that P is a more restrictive class, and that there are things that are in P that are not in P. And so it could be that these two classes are equal, that everything in P does in fact require exponential time on a deterministic Turing machine. But there's also another possibility, and that's that these problems that are in P can somehow be solved polynomially on a deterministic Turing machine and do not necessarily require exponential time on a deterministic Turing machine. So one of these two cases must be true, but it's not known at this time. There is no proof for either one of them, although it's really looking like the first case holds. So let me end this video with a look at my so-called language onion. Remember, we had regular languages, context-free languages, and decidable languages. And going up, we have languages that are Turing recognizable, and some of those languages are not decidable. Above this class of languages, above the decidable class of languages, are the languages that are not decidable, and some of them are Turing recognizable, and some of them are up in this area, and they are not Turing recognizable. So now let's look more closely down here at regular languages. All of these regular languages can be decided in linear time, by the way. And here we have context-free languages, and those can be decided in order n cubed time. And these are all proper subset relationships. Here's the class P, and here's the class exp time. This is the class of problems that can be solved in polynomial time on a deterministic Turing machine. And these are the problems that can be decided in exponential time on a deterministic Turing machine. And we have also the class NP, and we don't really know how to draw the bubble for that. It's most likely the case that it is the same as the class of problems that require exponential time on a polynomial Turing machine, but this is not proven yet, so that's why I have a question mark there. So it's probable that those two are the same set. So this is our language onion, and again, notice that these questions about P versus NP are all sitting in here between the class of order n cubed, for example, which is a kind of polynomial language, and the set of all decidable languages.